it can be a little hard to really have a good mental image of what a linear transformation is doing other than just somehow transporting you from one vector space to another. But we know that for finite dimensional vector spaces, the isomorphism classes are the Euclidean spaces represent the isomorphism classes of finite dimensional vector spaces. So we can picture what a linear transformation is doing, or what a linear map is doing, by looking only at examples of linear maps that go from one Euclidean space to another. And of course, the Euclidean spaces that are easiest for us to visualize are R2 and R3, and R1, I guess, because those have dimensions small enough that they fit into our physical space. So let's look at an example of a linear transformation from R3 to R2 and see what its null space and its image actually look like, to kind of see how they can fit together, or how it's possible for them to fit together. So here's a map from R3 to R2. It is linear. I won't prove that it's linear, but it is. So to think about its image and its rank, let's write all of the actual outputs that it produces as a span of linearly independent vectors, so that we know what the rank of this linear map is. So this is, right, if we parameterize this, this is A times 3, 6 plus B times -1, -2 plus C times 1, 2. Well, you can see that these three vectors are actually, they're all scalar multiples of each other. So since we're after a basis, we can actually throw away any two of them. So let's, I guess I'd rather keep this last one just because the entries are easier. So the image of this function is actually spanned by just the single vector 1, 2. Right? These other variables are just giving us other ways to come up with vectors in the span of 1, 2. So as a result, the rank of this is 1. Okay, so what about on the null space side? So to know the null space of this, we have to set this equal to 0. In other words, set it equal to the 0 vector in R2. So 0 equals 3a minus b plus c, 6a minus 2 plus 2c. Okay, so to solve this system of linear equations, right, this is really 3a minus b plus c equals 0, and 6a minus 2b, there should be a b here, plus 2c equals 0. We can write down the corresponding coefficient matrix. 3 minus 1, 1. 6 minus 2, 2. Of course, you might notice that this coefficient matrix is actually the same as just those coefficients, which is not a coincidence. That's something that we'll get to later. But row reducing this, right, we get 3, I guess, to get to reduced row echelon form, we need to divide this first row by a third. So 1 minus a third, and then zeros. Okay, so this says that A, B, and C, A is not free. A has to be minus a third B, plus a third B, minus a third C, and then B is free and C is free. So this is B times, I guess, a third, 1, 0, plus C times minus a third, 0, 1. So the span, all right, so the null space of this map is spanned by these two clearly linearly independent vectors, just because of where the 1s and 0s are. 1/3, 1, 0, and minus 1/3, 0, 1. Okay. So the nullity of this is 2. Okay, but let's actually draw a picture of what is happening in R3, and then mapping us over into R2. So I'm not going to be too exact about what our picture looks like, but I'm going to draw the general geometric situation. So in R3, right, we have, so not sure how to draw R3 in general, maybe just 3 coordinate axes. Actually, I'm just going to sort of leave our R3 blank right now, because I'm going to draw some stuff in here in a minute. And then our function transports us to R2. R2 is a little easier to draw on the screen because it's a plane, so I can just draw this. Okay, and the image, so I might have coordinate, let me draw some coordinate axes in R2. In R2, our image is the span of the vector 1, 2. So this we can draw. The vector 1, 2 looks like this. And so the span of that is this subspace. So this red line here, this is the image of the map. Okay, now over in R3, the null space is spanned by these 2 vectors. So what geometric shape do 2 vectors span? They span a plane that goes through the origin. So if the origin is here, right, these 2 vectors might span, say, this plane. Okay, in R3. Now, all of this stuff in the blue plane here gets mapped to 0 over in R2, right? Because this blue plane is the null space of F. Okay, so in the rest of R3, so if you look at what we have so far, remember the red over here are all of the outputs that this function actually takes on. Well, this blue plane here only covers this single output at the origin. So that means to get all of the other outputs, we must have to move off of this plane. So if we move up to, say, this parallel plane up here, any vector up in this plane will give us some other output. And then if we go down, say to this plane down here, any vector down in this yellow plane might give us this output over here. So all of these parallel planes, translating sort of up and down in R3, all of these parallel planes will produce all of these outputs along this image. So you can actually sort of see that it's almost as if these planes are acting like a copy of the image, but somehow sitting over in R3. And if that's the case, then, and that is the case, then you can really see that if the null space here has dimension 2, moving back and forth in the last remaining free direction is what's tracing out the image. Well, that means that the dimension of the image, right, this one-dimensional image, together with the dimensionality of our null space, those have to fill up the entire domain space. So this has to be 3 in this case, because it's R3, right? So the dimensionality of our null space plus the free dimensions that let us move out of the null space will give us, sorry, I've said that backwards. So the free dimensions that are left over after sort of drawing our null space, those dimensions kind of have to trace out the image. And so the 2 added together have to fill up the entire Euclidean space that we started with. So this kind of makes you wonder, right? So this is just for this particular example, but this makes you wonder, so the dimension of the image, this is the rank. And the dimension of the null space. This is the nullity. And this 3 was here because that's the dimension of the domain space. So, in general, if we have a linear map from F to W, the role of 3 would be played by the dimension of V. And what we're seeing here is that maybe if you add the rank and the nullity of a map, maybe you get the dimension of the domain. Right? We've only checked it for one particular example, so this isn't a proof or anything. This is something that we'll have to prove if we think this is right. But this example sort of gives us, on the one hand, it gives us a way to visualize what linear maps do. They somehow squash down the null space, but sort of in the process, they also squash down all of the other parallel planes into, right, a single point, or a collection of points depending on the image, right? But also this example makes us think that maybe the rank of a map plus the nullity of the map is equal to the dimension of the domain. So since we have this idea that this might be true, now we should go looking for a proof.